Spoke earlier about EME, and sometimes the question that comes up is tracking. How do you keep the antenna pointed at the moon? Moon's about half a degree wide, and I have an antenna that's about 2.5 degrees beam width, so you want to actually point at the moon. So in the spirit of doing everything yourself, I decided to go build a tracking system, and let's see how it works. So need to keep the antenna pointed at the moon. And WSJTX, if you're familiar with it, actually does calculate the moon as L. So it does that when you're in the tracking mode, it will do that. Or you can use a standalone tracking program. And you need some form of sturdy position or motor control. So I don't know if you're familiar with it. Slew drives are the sort of the big daddy of tracking controllers. You can see a bit of one there, and you can see the moon in the bore sight of an old rifle scope I've attached to it, so I can see how all this works. You can see the slew drives behind the dish on the left-hand side, and they were originally designed for moving solar panels around to track the sun. This is actually an as over L, or elevation over azimuth. So that's how actually I move the antenna on the system. They're a 24-volt gear reduction motor. It's got a planetary drive of about 500 to 1, and then it's a 60 to 1, I think. Ratio follows that. So give it like a 30,000 to 1 gear reduction in this thing. Then there's a quadrature encoder on the back of it, which actually tells you where the motor is. So once you've set a reference, you actually can get the position information back. So what we did is we built our own controller for it. So you can see the unit on the photo here. In the foreground is the CPU board, which uses an Atmel 1284, which is a little 8-bit CPU. And it has a PWM output for pulse width modulation. And the board in the back is the power electronics board, which basically has 2 H bridges, which drives each of the motors. So it's a DC motor. And by turning on one side more than the other, it'll actually go either direction. And what the duty cycle is will tell you how fast you go. And if you get the feedback for the position on from the quadrature encoder, we have a little quadrature decoder chip in here that gives me back the number of pulses. You can actually build a complete control loop around it. And we built a PID feedback system all running on it. And then while we were at it, we put Ethernet on it. You figure, well, how do you get Ethernet on such a small processor? Well, there's a chip called a Whiz 5500, and some of you in the Arduino world will have might know about it. And it's actually got a TCP/IP stack in it, and it talks to a SPI bus. We put the whole thing together and put free RTOS on it, and we run that as a real-time control system. So in the Ethernet, we have a socket. It takes ham-lib commands in for a rotor control. We interpreted that, run a PID controller, and we actually point the antenna with it. So what happens is any code that can handle that format, we can actually point the antennas on it. So that was a little homebrew project. You can see it's built on an Oshpark board, and you can do reflow at home. You can get a cheap, inexpensive reflow oven. I bought one for about $300, and that's what makes these boards. So it does a pretty good job of it. So then we wrote our own tracking program as well. There's an ephemeris library called PyFM. It's in Python. So we put a wrapper around it and got it to talk via TCP to some other functions. And then we put a little display system on it. So when you call it up, it'll actually give you a display in real time, tracks the moon across for you and shows you what's going on. So I'll show you a little video here of what it looks like when it tracks. Let's see if I can find it. And there it is. So let's see. So this is a time lapse. I put a camera on the scope and I let it run. So about every 2 minutes, it's taking a picture, and you can see the background moving. So that's actually calculating the moon position and then moving and keeping the scope trained on it. There's no optical feedback. That's just the motor positions based on calculated positioning information. So that's how I keep my antenna pointed at the moon for hours at a time while I'm trying to do EME. We'll run it one more time, and then everybody gets to see it again. So you can do it. You can build a pretty interesting little control system for doing stuff like that. So that's my 2-minute lightning talk. Anybody got any questions?
I Actually, I do have one. Would
Sure.
there be any benefit to actually, doing it optically? as
You
opposed to-
can, the trouble is, it's really hard to see the moon when it's overcast. It's really hard to see the moon when it's at a new moon position because the sun is somewhere similarly in the place in the sky, but the antenna beam width is narrow enough. I don't see the sun, but I can't see the moon because it's washed out by the sun. It's facing the wrong direction. So, yeah, you could do it optically if you can see it. There's computer vision. I've got another question back there.
Yeah, I think your antenna is a portable one. What do you
Yep.
need to do to calibrate it in a
Oh,
new
that's
position?
why I look at it optically. So the way I start out is I put the antenna up, I have a level on it and I level it out. So I've got a horizontal plane that's correct with respect to gravity, basically. I lock it down on that situation and then I take a compass, just use my phone's compass. That's all I use. Compute what the declination is in the area, which where I'm at in Oregon is about 16 degrees. And I compute a nominal true north-south bearing and I set the rotor to that. So I know I'm level and I'm roughly true north-south. And I wait for moonrise or I can see the moon and I tell it to go to it optically. And then I look at it. It's what the rifle scope attachment's for. I stick it on the mounting clamp and then I tweak it a little bit. The software's got a provision where I can jog it. So I dial it into the center. Then I'm all lined up and then I put the antenna on and go from there. If I take the feed out of the antenna, I can look through the bore sight of where the feed goes in and I can see that the moon's in the center of that as well. So I do an optical check. And then after that, I don't have to worry about it. It's actually quite stable. If I, leave the system up, park the antenna or take the antenna off, come back the next night and check it again, the moon's right dead center. So the system keeps its position quite well. So it's really bad at the mechanics on it. So it works pretty good.